Hello friends, here is a JASPREET Kaur from the Department of Mathematics from the School of Engineering and Technology. Today I am representing my presentation on the topic of the complex number in front of you. So let's start the topic. This is a complex numbers, as we know that this is the study of the mathematics in the iota form rather than the real numbers, because these are the numbers which are introduced from the different field. So let's start the PPT. First is what I included in this PPT, that is the topics I included. First is the introduction, that is the fundamental operations of Z, like as addition, subtraction and multiplication and subtraction of the complex numbers. Then is the conjugate of Z. Conjugate is the term of complex numbers which gives the another form of complex number like as the opposite of that one. Second is the geometrical representation of the complex number. I will plot it in the xy plane as it is in the graphical representation of the complex number. Third one is the polar form of rectangular form. This is the iota's cis theta form, like as I elaborate in the cos and sine. So this is the polar form, or maybe say as the rectangular form of the Z. Fourth is the modulus and argument. It is gives the real value of the Z, that is the modulus, and argument is the angle of the y and x plane. Next is the equation of the complex number in the circle. As we know that the xy plane has an equation of a circle in the real form, but today I am representing it in the complex form also. My last topic is the stereographic projection. My whole PPT is concentrated on this topic because I think stereographic projection is the main part of the complex numbers, because it has various applications in the complex number. Let's start the topics. First one is the introduction. This is the number a plus iota b form, where a and b are the real numbers and iota is our complex number called as iota. Don't call it as a I, it is a iota. As this a number of the form a plus iota b is called the complex number, where a and b are the real numbers. So it may be also represent as an ordered pair of the real numbers, that is a and b, as I given it as a z equals to brackets of a comma b, where a and b are the reals and brackets represents the complex numbers. Here a is the real part and b is the imaginary part of Z, and we can denote it as a RE or IM for real and imaginary respectively. So if Z equals to a plus iota b, then I can also say that Z equals to a comma b as an ordered pair. Then my real part of Z is a and imaginary part of Z is b. If I take in the cases of the complex number, that is b equals to 0, then my Z is left with the a, then I can say that Z is purely real. And after that, if I am taking the a equals to 0, then I can say that Z equals to iota b, means Z is purely imaginary part. So this is the introduction. This is the theory which is given by the Leonard Eilers in the mid of 17th century. So let's start the fundamentals operations of Z. This is the addition of two complex numbers is again a complex number. We can easily take it as a Z1 and Z2 with the defining as A1 plus iota B1 and Z2 as a A2 plus iota B2, and we can add it as Z1 plus Z2. Then we can left with the real part as A1 plus B1 and iota with the imaginary part having B1 plus B2. So addition of two complex number is again a complex number. Similarly for this subtraction, that subtraction of two complex number is again a complex numbers. Now the multiplication, we can take it as a Z1 into Z2. It will gives us a A1, B1 as a real part in the multiplication and B1 and B2 as a imaginary part in the multiplication. So multiplication of two numbers is again a complex number, and division of two numbers of complex form is also gives a complex number. We can take it as a z1 by z2, then we can get the a by b and plus of iota c by d, where a plus iota c is my z1 and z2 as a b plus iota d. So these are the fundamental operations of the complex number. Next one is our conjugate of complex number. This is like as a opposite of the complex number, and every complex number is in the pair, because if there is a positive value then there will also be a negative value. That is the z. If z equals to iota a plus iota b, then I can say that its complex is a conjugate is a minus iota b. That is denoted by the z star, or I can also write it as a z bar. So if my z equals to a plus iota b, then my z conjugate equals to, or z star equals to, a minus iota b. We are just taking the sign positive to negative or negative to positive. I am taking the example like z equals to 4 plus iota 6, then my z conjugate is 4 minus iota 6. So I can write it as a z star, z bar, or con of z, that is a conjugate of z. Second one is my for the negative part, z equals to 3 minus iota, then I can say that z conjugate is 3 plus iota. So it is the form which I can taking as a positive to negative and negative to positive. So this is the conjugate of the complex number. Next is the properties of these conjugates, as the first one is the conjugate over conjugate gives the same number. Like as in the previous example, I can say that z equals to 4 plus iota 6, then I can taking the conjugate, it will becomes the 4 minus iota 6, and again taking the conjugate, it will becomes the 4 plus iota 6 again. So conjugate over conjugate is a z. Then I can also write the real part of z as half of z plus z conjugate. Taking the z as a plus iota b, then conjugate is z a minus iota b, then taking the addition of then iota b and iota b's are cancelled, I will left with the 2 of a, that is the real part, and 2 will cancel with the half, so it is the real part of z left with the a. Also the imaginary part of z equals to half of iota of z minus z conjugate. Taking the same example, z equals to a plus iota b and a minus iota b, then taking the subtraction of the both, then I will left with the iota 2b. Then 2 is cancelled with 2 and iota will cancel with the 2 and iota. So left with the imaginary part of z, that is b. Third one is z equals to z conjugate if z is purely real. In the verb point I discussed that real part of z is a, so z equals to z conjugate, because there is no any sign change of the sign. So if z is purely real, then conjugate equals to the z also. Fourth one is z equals to minus of z conjugate. It is either if z is 0 or purely imaginary. Like as iota of b, then I can taking the conjugate, that will becomes the negative of z. So you can also say that minus of z equals to z conjugate if z is purely imaginary or 0. My fifth point is for the two complex numbers z1 and z2 has a addition and subtraction property with combination and also with the individuals. Like as I am taking the z1 z2 whole conjugate, it will becomes as the z1 conjugate and z2 conjugate individually. Similarly for the negative part, z1 minus z2 conjugate equals to the z1 conjugate minus z2 conjugate. You can easily take the example for that as taking the z1 as a1 plus iota b and z2 as a a2 plus iota b, and add them, subtract them, the answer will be same as given. Similar for the product and the quotient conjugate complex numbers. Next one is my geometrical representation of z. I will plot it on the xy plane taking the coordinates x and y from the coordinates. Here I am taking the y as a real part and x as a iota part. So if my z is a p point, that is x comma y, then I can write it as a z equals to x plus iota b or p of xy also, because it is a rectangular form of the z. Now my z conjugate, it will becomes the x minus iota y. So that my x is the real part, it may be written as the half of z plus z conjugate, and y is my imaginary part, it will be written as a half of iota z minus z conjugate. Therefore, these are the Cartesian coordinates of the points. X and y may be written as the half of z plus z conjugate and half of 2 iota z minus z conjugate. As I write the z equals to xy, so I can write it in the Cartesian coordinates, half of z plus z conjugate and half of iota z minus z conjugate. This representation in the plane is called a Argand diagram. It is also given in the questions and may be clear more in the questions. The plane is called the complex plane, Argand plane and the Gaussian plane. You may also write it in the questions like complex plane, find the complex plane and find the Argand plane also. Next is the polar form of z. Here I am taking the polar coordinates, that is r and a. You can also skip the a by the theta, as many mathematicians use it as angle theta, but I am taking it as a. As my perpendicular is the y and my base is the x with the hypotenuse of r, there is a right angle triangle PMO having a polar coordinates r and a. Then my cos theta will becomes equals to x by r, that is the base by hypotenuse, and my sin theta equals to perpendicular by hypotenuse, that is y by r. So I can eliminate the value of x and y as x equals to r cos a and y equals to r sin a. So my z becomes the x plus iota y. Put the value of x as r cos a and y as r sin a. So my z becomes the, taking the r common, it will becomes the cos a plus iota sin a. This is the cis theta form, where c is the cos theta, I is the iota and sin is the s. It may be also written as a cis theta form and e raised to power iota a form, exponent form. So my polar form becomes the r e raised to power iota theta or a. It is called the polar form of the complex number z. Next is the modulus and argument. Modulus gives us the real part of the complex number. We are taking the coefficients and give the square of them, and after that add them, then we get the value of the modulus. In the polar form, complex number is r, where is the modulus or absolute value gives the real value of the z. A is called the argument or amplitude of the z. It is denoted by the argument of z arg and amplitude of z, that is amp. So mod of z equals to r, which is equals to under root of x square plus y square. This can be easily transferred from the Pythagoras theorem, that is r square equals to x square plus y square, that is Pythagoras perpendicular and hypotenuse. Next is my argument of z or amplitude of z. This is the angle of tan theta, that is tan inverse y by x. So the value of arguments which can satisfy from minus pi to pi becomes the principal value of the argument. That is the, I can say that minus pi to pi satisfy the principal value of the argument. These are the certain cases of the principal values, but I am not discussing right now because this is a basic form of the complex numbers. So my next is the example of these all topics, that is conjugate, polar form, moduli and principal values with argument. First one is my complex conjugate of 2 plus 5 iota square. Taking that as a identity 2 plus 5 iota square having identity a plus b whole square, that is equals to a plus b and a minus b. So my questions become 2 plus 5 iota into minus 5 iota as a plus b, a minus b. Taking the squares, then it will becomes the 4 minus 25 as a real part, and with the imaginary part 10 plus 10. So my first complex number becomes minus of 21 plus 20 of iota. Now the question is the complex conjugate. So I am taking the complex conjugate of the square, that is equals to minus of 21 plus iota 20's conjugate equals to, then I am easily change the sign from plus to minus, that is minus 21 to minus of 20 iota. Taking to the next question, that is express the 1 minus 2 iota into the polar form. Let's taking firstly z equals to r cos theta plus iota sin theta. So 1 minus 2 iota is equals to r cos theta plus iota sin theta. It may be also written as r of e raised to power iota theta. Taking the real part and imaginary parts, then 1 equals to r of cos theta and minus of 2 equals to r sin theta, where r cos theta and 1 are the real parts and r sin theta equals to minus of 2 is the imaginary part. Now squaring these two, then I will left with the r square cos square theta plus sin square theta equals to 1 plus 4. As cos square theta plus sin square theta has equals to 1, because there is identity, sin square theta plus cos square theta will becomes the 1. So I will left with the r square, that is equals to 1 plus 4, 5. So r square equals to 5, taking the square in the under root form, then r equals to under root 5. This is our modulus. Now dividing 3 and 4, where 3 is the sin theta equals to minus 2 and cos theta equals to 1. Then dividing sin by cos, that equals to tan theta, r and r are cancels, minus 2 by 1. So tan theta equals to minus of 2, then theta will become the tan inverse minus of 2. As we know that tan has a no any value, so I cannot change it into the radian form. I can take it as a real form in the 2 also. So taking the negative outside the tan, minus of tan inverse 2 equals to the, so my complex number becomes the polar form, that is equals to r of cos theta plus r of sin theta iota sin theta 1 minus 2 iota equals to under root 5 r e raised to power minus iota tan inverse 2a, that is e raised to power iota theta form. So this is the polar form of the 1 minus 2 iota. Find the modulus and the argument. This is the next question. Minus 5 plus iota 5. Taking the firstly z, let's taking it as a z, then mod will becomes the square of the x and square of the y, where x equals to minus 5 and y equals to similarly minus 5. Taking the square of both, it will becomes the 25 plus 25, then it will becomes the under root of 50, and we can change it into the 5 under root 2. Now taking multiply and divide the whole z by the under root 2, and taking the common 5 under root 2, then my form will becomes the minus of 1 by under root 2 plus 1 by under root 2 iota. Taking the 5 under root 2 at the outside, as we know that cos pi by 4, that is the 45-degree value of the cos theta is the 1 by under root 2. Now there is a change like pi minus pi by 4 in the angle, same as the sign for pi minus pi by 4. Why we can do this? Because we have to find the negative, neglect the negative value, and we have to change the quadrant of the both, because pi minus 5 by 4 will becomes the 45-degree, and in that quadrant cos and sin both have a equal sign, that is the positive sign. So pi minus pi by 4 is only for the positive value. So it will becomes the 5 under root 2 cos of 3 pi by 4 and plus of iota sin 3 pi by 4. This is my modulus and argument of the 5 plus iota 5. This is all over done. Next is my equation of the circle, another topic of the complex numbers. Here I am taking the circle C with the point at center P1 and Z1, and the radius of this center is the r. Let taking the p of z any point on the circle boundary, that is a p of z, as I given in the diagram, that p1 and z1 is the my point of center, r is the radius, p of z is the my point on the circle's boundary. So length of any line p1 p equals to the radius of the circle. Length of the line is z minus z bar equals to r. Taking the square of the both, that is z minus z1 whole square equals to r square. Now we have the property of the conjugate, that z into z conjugate equals to the mod of z square. So I am using that same value here, z into z conjugate equals to z square. So z minus z1 and z minus z1 conjugate equals to the r square. Now multiplying the both the brackets, then I will becomes the z into z conjugate minus z1 conjugate or into z, and minus of z into z1 conjugate, and left with the only the real part as a z into z1 conjugate. It will becomes the mod of z1 square, and taking the r square in the left side, that is mod of z1 square minus r square as a real part, taking it as the common, equals to 0. This is a constant term. Now taking the b equals to minus of z1 and z1 square minus r square as a c, because this is the constant term. So I am taking these values to generate a general form of equation, form of this circle's equation. So my verb equation becomes the z into z conjugate b of z plus b of z conjugate plus c, where c is the z1 square minus r square and b is minus of z1. So I am taking the whole equation in the positive form with the coefficient of the 0 and the equation of circle in the general form. This is the equation of the circle in z, that is in the complex form. Next is the example of the equation of circles. You may easily understand this these all the derivation in the example. As my first example, the find the loci of the point of z satisfying the following conditions. First one is z plus 1 is greater than or equals to 2, and second one is z minus 1 by z plus 1 is less than or equals to 2. So solving the first, z minus 1 is greater than or equals to 2. Again I am taking the z as a x plus iota y. Then the real part and imaginary parts I will separate it, and that is x minus 1 plus iota of y. Then it is a mod, so I am taking the square and taking the under root also, x minus 1 whole square plus y square greater than or equals to 2. Taking the square on the both side, it will becomes the x minus 1 whole square plus y square is greater than or equals to 4, which is representing the circle's equation. This is the exterior because the greater point represents the exterior form of the circle, but the boundary point of the circle is x minus 1 whole square plus y square equals to 4. So this is which will represent the equation of circle of exterior and boundary both. Now my second question is the z minus 1 by z plus 2 less than or equals to 2. Taking the mod on the upper denominator and denominator also, that is equals to z minus 1 mod by z plus 1 mod greater than less than or equals to 2. Taking the z plus 1 on the right hand side, z minus 1 mod is less than or equals to 2 mod of z plus 1. Squaring on the both sides, because we have only the form, why we are squaring, we have only the form to eliminate the under root by the mod. So we are taking the square again and again. Z minus 1 whole square will becomes the z minus 1 whole conjugate. As 1 has no any conjugate because the complex number has the conjugate, so it will takes the over the z only. My z minus 1 whole square becomes the z minus 1 z conjugate minus 1, and my z plus 1 whole square becomes the z plus 1 z conjugate plus 1 in the right hand side with the coefficient 4. Now solving these both brackets, that is z into z mod minus z into z conjugate plus 1 less than or equals to 4 z into z conjugate 4 into z plus z conjugate plus 4. Eliminate the z into z conjugates on the other sides, and after solving that, I will left with the 3 of x square plus y square plus 5.2x plus 3 is greater than or equals to 0. This is after the solving the whole terms. My z into z conjugate will becomes the z square mod of z square, that is the x square plus y square, putting the values, and my z plus z conjugate gives the real part of the equation, that is the x, and my 3 is left with the constant. So this is the equation of the circle which represents the exterior, and the boundary of the circle is x square y square plus 10 by 3x plus 1 equals to 0. So this is the equation of circles questions. Now the region of the argand plane satisfies the conditions z minus 1 by z plus 1 by less than or equals to 2. That is the same question I am taking in the argand plane. So solving this, here I am not taking the z as a x plus y iota y because it will become the complicated, so I am taking it as in the form of z originally. So solving the same sum by the same form up to the 3 z into z conjugate minus 5 iota z minus z conjugate plus 3 less than or equals to 0. That is above steps are the same as in the previous question. So z into z conjugates becomes x square plus y square because this is the mod of the square, mod of z square, and my z minus z conjugate will becomes the imaginary part of the z, that is the 2 iota y, putting the values these. So my equation will becomes the 3x square plus y square minus 5 iota 2 iota y plus 3 less than or equals to 0. Now solving again the iota into iota, then it will becomes the 3x square plus y square plus 10y plus 3 less than or equals to 0. So this is the equation which represents the equation of the circle. Now next question is for the locus point on z, as my condition is z minus 1 plus z plus 1 equals to 3. Solving this question is by the form of x plus iota y. You can also be solve it by the scaling in the another form, but I am scaling solve as the x plus iota y as the given. Taking the z as x plus iota y minus 1 and the another z plus 1 equals to x plus iota y plus 1 equals to 3. Now taking the mod of the both x minus 1 whole square plus y square and x plus 1 whole square plus y square again equals to 3. Taking the x minus 1 whole square plus y square equal on the other side, that is equals to the x plus 1 whole square plus y square equals to 3 minus x minus 1 whole square plus y square under root. Taking the squaring on the both sides because we have to eliminate the under root because we cannot solve easily by the under root. So taking the square on the both sides, and the right hand side will becomes the a minus b whole square, and that is equals to the 9 plus x minus 1 whole square plus y square minus 6 of under root x minus 1 whole square plus y square. I am taking the again square to eliminate the again under root. So solving the whole equation, 6 under root x minus 1 whole square plus y square equals to 9 minus 4x. Again squaring, 36 x minus 1 square plus y square equals to 9 minus 4x whole square. So solving the squares parts and other parts, after that I will left with the 20x square plus 36y square equals to 45. That is the last second step of the equation. So taking the 45 on the other side, that is 20x square by 45 plus 36y square by 45 equals to 1. After cancellation, I will left with the x square by 9 by 4 plus y square by 5 by 4 equals to 1, which will represent the ellipse. So this is the Loki point of the ellipse. Now these all are the question. That is my last topic which I whole concentrating the whole complex number my topic on the stereographic projection. This is the projection like as the if I am taking a plane and sphere and meet it with the line on the point intersecting. So this is the stereographic projection. Let's begin with the as n is the point and p dash is my point on the plane and is a point on the sphere, and the line joining these two will gives us the stereographic projection of the whole content. So what is the stereographic projection? It is the projection mapping the projects the sphere on the plane. So it may be taken as the by the point to point correspondence, or we can say that 1:1 correspondence of the plane and sphere. I can also describe the theorem for the stereographic projection in the next slide. We firstly consider the sphere, unit sphere in the Cartesian coordinates, which is given as the x square y square plus z square equals to 1. I am taking it is in the 3D form because there is a sphere, not a circle. Circle is on the boundary of these all. So taking it in the complex form as a 1 minus 1 iota minus iota and 0 to infinity as a third coordinate. So my equation will become the x square y square z square equals to 1 again, and is the my points on the this locus point on the north pole, taking the m as a here denotes the remainder of the sphere. So this is the stereographic introduction. Now there is a theorem which is most important theorem on the stereographic projection, that is the map from z to. This is the coordinates of x, y and z. X equals to z plus z conjugate y, 1 plus z mod of z square, and y is the z minus z conjugate y, 1 plus mod of z square, and z is the z square minus 1 by z square plus 1. These are the x, y and z coordinates of the map. Z to the this map is the 1:1 correspondence between the circle C and the sphere x square y square plus z square with the unit radius 1 in the R cube, excluding the points 0, 0 and 1. This is the north pole of the sphere. So this is the statement. I hope you really understand it, and let's start the proof of this theorem. Taking the S as the sphere with the unit radius and the center at the origin. This is my diagram. You can easily understand the diagram. Taking the sphere on x, y, z plane with the origin O, and y is the my point on the sphere and p is the point on my plane. This is mainly the stereographic projection is for the plane and sphere's interaction by the pointwise interaction. So sphere is a unit radius and my v is the point joining the sphere to the plane. Let p be the any points on the sphere and p dash be the point on the xy plane. So vp meets the plane, v and p meets the plane. Since p is the point on the sphere and center is the origin with the radius of unity, so my sphere's equation will become the x square y square plus z equals to whole 1 with the unit radius. Since the point is v 0, 0, 1, which I am taking the n north pole, and p is x, y and z, and p dash is x, y and 0. Both are the collinears. These all are the collinears v, p and p dash. All are in the same line, as we can see that in the diagram easily. Now as this is the equation of intercept form, so my capital X by small x equals to y, y by y, that is the capital Y by y equals to z minus 1 by minus 1. This is the form from the 0, 0 and 1 coordinates. So this is my intercept form. This is all are equals to the k, any constant we can say it as a k. So eliminate the value of x, y and capital Z of the sphere coordinates, that x equals to k of x, y equals to k of y and z equals to 1 of k. These are the coordinates of the sphere. Put these values in the equation of the sphere, that is x square y square plus z square equals to 1. Putting the value of x equals to kx, y equals to ky and z equals to 1 minus k, and taking the square of all, then the equation will becomes k square x square plus k square y square plus 1 minus k whole square equals to 1. Taking the common k, then I will left with the x square plus y square plus 1 equals to 2 of k. Then find the value of the k and k cancel, then k equals to 2 by x square plus y square plus 1. Put the k value in the above x, y and z coordinates of the sphere. Then x will becomes the k of x, that equals to 2x by x square plus y square plus 1 equals to 2z plus z conjugate. Because the 2x equals to the this is the real part, and we can say that the real part equals to half of z plus z conjugate. So my z plus z conjugate will becomes the 2x. So this is and x square plus y square is the mod of the z and square of that. So putting these all values, my x will becomes the z plus z conjugate and 1 plus z mod of the square. Similarly for the y equals to k of y, put the value of k as 2 by x square plus y square plus 1. So y is my imaginary part, so I can return it as a z minus z conjugate, that is equals to the 2y, and x square plus y square as a mod, that is mod of z square. So my whole the coordinate of the sphere of y will becomes the z minus z conjugate 1 plus mod of z whole conjugate whole square. And last one is my z equals to 1 minus k. Putting the value of k, after that solving x square y square as mod of square, and we can get the mod of z square minus 1 by mod of z square plus 1. So these all are the x, y and z coordinates. I can write it as the spherical values of the coordinates of the sphere x, y, z in the form of x and y sphere coordinates, as in the last of the map z becomes the equal 1 1 corresponding between the c and the sphere. But we have to form the intercept form also in the iota form. So z may be written as the x plus iota y, that is equals to x by 1 minus z plus iota y by 1 minus z. Taking the 1 minus z in partial form into the combined form, that will becomes the x plus iota by y 1 minus z. This is the my complete complex number, but the given complex number z on the xy plane correspond to the sphere coordinates, that is x, y and z. So this is the theorem of the stereographic projection. I think you will understand it very easily. So this is my stereographic theorem. Let's taking the examples of the stereographic projection. First one is it describe the curve on the sphere to which any straight line on the z plane correspond. Means we have to correspond the z plane to a straight line on the xy plane. Let's start the solution of this question. Taking the equation of the straight line on in the z plane, that is alpha bar plus z plus alpha into z conjugate plus r equals to 0. This is the standard equation of a straight line, and where alpha is the complex constant and r is the real number. Say alpha equals to, as it is a real number, I can also take it as a plus iota b in the complex form, where a and b are my real numbers. If z is the if there is a point taking p as x, y and z point on the sphere which correspond to the plane z, because we have to find the lines correspondence to the z plane, as xy plane correspond to the z. So I am taking the by the point wise correspondence, taking the point of sphere as x, y, z, and complex plane has a point z equals to x plus iota y by 1 minus z. Substitute the values of z in the first equation, that is alpha bar z plus alpha into z bar plus r, that is the equation of the straight line. Put the values of z in that equation. So alpha bar x plus iota y by 1 minus z plus alpha into x plus iota y by 1 minus z whole conjugate plus r equals to 0. Solving the equation, then taking the 1 minus z in the, multiplying the whole equation by 1 minus z, then alpha bar x plus iota y plus alpha into x minus iota y plus r 1 minus z. Here taking the conjugate of the x plus iota y in the second term, that is x minus iota y. Taking the common x from the, then I will left with the alpha plus alpha conjugate becomes the coefficient of x, and with the imaginary part alpha minus alpha bar with the coefficient of y, and the constant term r 1 minus z whole conjugate equals to 0. After solving that, we will becomes the, in the equation will becomes the 2ax plus 2by plus r into 1 minus z equals to 0, which represents the planes passing through the 0, 0 and 1 point, because 1 is from the 1 minus z, that will represent the z coordinates. So this is the required curve. We have to find the sphere correspondence or interaction with the line, that is the plane. Second, 2ax plus 2by plus r into 1 minus z equals to 0. So this is the required curve of the sphere, is the circle on the sphere passing through the point 0, 0 and 1. This is the question of the stereographic projection, and we can elaborate it. My next question is, find the spherical representation of the complex number z equals to 4 minus 3 iota. Here I am gives the x plus iota y as a 4 minus 3 iota. So x equals to 4 and 3 is minus 3 is as y. We have to represent it on the Riemann sphere, or you can identify it from the Riemann sphere. This is a question of the stereographic projection. So my z is 4 minus 3 iota, and its conjugate will becomes the 4 plus 3 iota. So both having the addition, z plus z conjugate equals to 8, that is the real part of the both, and z minus z conjugate equals to minus of 6 iota, that is the imaginary part of the both. And mod will becomes the square of coefficient of x, that is real part, and mod of square of y, that is the imaginary part. So my mod will becomes the 16 means 4 square plus 9 means 3 square. 16 plus 9 25. So my mod will becomes the 25. Put the values of these all the equation. These are values in the x, y and z coordinates of the Riemann sphere corresponding to the complex number z. Then my x equals to z plus z conjugate by iota 1 plus mod of z square, that is equals to 8 by 1 plus 25. Here I am just putting the z plus z conjugate value 8 and mod of z square value 25. So my x will becomes the 4 by 13. Next is the y equals to z minus z conjugate by 1 plus mod of z square. So it will becomes the minus of 6 iota by 1 plus 26. Iota and iota are cancelled, so my y will becomes the minus of 3 by 13. Last is the z coordinate, that is mod of z square minus 1 over mod of z square plus 1. Put the value of mod of square, that is 25. So upper equation will becomes the 25 minus 1 and denominator will becomes the 25 plus 1. So it will becomes 24 by 26, that is 12 by 13. So my xy and z coordinates of the Riemann sphere will becomes now 4 by 13, 3 by 13 and 12 by 13. These are the points of the Riemann sphere which corresponding to the point 4 minus 3 iota on the complex plane, because this is easy question because we have given the complex number 4 minus 3 iota. So we will definitely corresponding the Riemann sphere to the complex number z easily. Now the applications of the stereographic projection, where the stereographic projection is used. First is the cartography. This is the cartography is the normal form of the drawings that like as architectures makes the drawings, as also there is a design of the building also be made by the cartography. Then this stereographic projection is used in the cartography, where Like as if we want to build a building, then we have to see the edges of the building. So these will be the projected by the stereographic projection. So it will be used in the cartography. Second one is the crystallography. Crystallography is, as we know that there are many crystals like as diamond, like as other sapphires having the edges or having the planes, different planes. Then the stereographic projection provides a mean representation of different planes and directions of a crystal in 2 dimensions. So in the crystals we can use the stereographic projection for making the different planes and direction of the crystal. And third one, it is also used to play the plays with the buff net. Buff net I am describe it by use of the diagram. We can say that if we are want to play with the buff net as the opponents and with the 2 players, then we can use the stereographic projection there also. So these all are the application of the stereographic projection. This is whole my topic. As I am really glad to be you will definitely understand my the concept of the complex number and my stereographic projection. So very thank you to listen me, and I will definitely understand, you will definitely understand the whole content easily. Thank you so much.